Welcome ASs, this is lesson 2 for term 2 and we're going to start at chapter 14. You should already have gone through last term's work on chapter 13 and 14. So if you haven't done that, go there first and look at those videos and try and do some of the work. But I'm going to start with exercises in 14a and we're going to discuss what to do with these. Now, in question number 14a, number 1, they ask us to find the equation of a tangent and b, the equation of the normal that goes through the following equation at a certain point that they give. So number 1 said that y is x squared minus 4, and they told us that x is 1. Okay. So firstly, if we've got x squared minus 4, we're going to need the gradient function. Okay. So if y is equal to that, we want the dy dx. So the dy dx is simply 2x in this case. Now we know that the x is 1, okay, so that means that if I substitute x equals 1 into this, I get a value of 2. Now remember, this is the gradient of the tangent, but we don't just want the gradient of the tangent, we want to know the actual equation of the tangent. So we're going to have to write, since a tangent is a straight line, y must be equal to mx plus c, which you can see at the top there, which means that we've got 2x plus c. Okay, so far so good, but now we're going to need an x and a y value so we can find our c value. In other words, we need a point that is on this graph. Well, they already told us that x equals 1, but we don't know what y equals. Okay, so we're going to have to find y by substituting that into the actual point or into the equation. So if I put y in there, I get 1 minus 4, which is minus 3. So one of the points is 1 minus 3. In fact, that is the point at which this tangent meets the curve. So therefore, I can go and put this point now into the rest of my equation and say that minus 3 is equal to 2 times 1 plus c, which makes my c equal to minus 5. And now I can go and write out the whole of this equation. So my equation comes out to y is equal to, same gradient, 2x minus 5. There is the equation of the tangent that goes through the point 1 minus 3 in the sum. Okay, they also wanted the equation of the normal. Okay, so if we want the normal, we're going to have to do the same thing, but remember, the gradient of a normal, if the gradient was 2 for the tangent, the gradient of the normal has to be perpendicular, and that means it must make the value of minus 1 when you multiply it, so that gradient must be minus a half. So now we're going to write y equals minus a half x plus c. And of course, this must also go through exactly the same point as the last one. So we can say that minus 3 is equal to minus a half times 1 plus c, which makes my c equal to minus 2.5 or minus 5 over 2. That gives me a final equation here of y equals minus a half x. Sorry, let me erase that quickly. In fact, I'm going to erase the whole one up here as well. I'll write it up top there. Y equals minus a half x minus a half x minus 5 over 2. And remember, if you don't like it in that form, you can multiply the half or the denominator of 2 away by saying 2y is equal to minus x minus 5. Or if you want to take the x over, you've got x plus 2y equals minus 5. Okay, each of these are legitimate ways of writing that. Now, you should be able to do number 1 through to number 6 of 14a quite comfortably from there on. Okay, so let's just actually erase everything here. Okay, let's look at question number 7. Find the equation of the normal to the curve at the point where the curve cuts the y-axis. Okay, so we want the normal to the curve at the point where this curve cuts the y-axis. Well, firstly, we're going to need the gradient function again. So we know that y equals x squared plus 4x minus 3. The gradient function, or y prime, or dy dx, is 2x plus 4. We don't know the x value at which the curve cuts the y-axis, except that if we recognize that the y-axis means that the x value is always 0. You should know that. So therefore, the point that they're really saying is we want to know where x is equal to 0. Okay, so let's put in 0. That will mean that the gradient will be 2 times 0 plus 4, which happens to be just 4. Okay, so now we have our gradient. Y equals 4x plus c for the straight line. We need a point. Now we know that the x value is going to be 0. If I put 0 into the original equation, which is the one up there, we'd get a minus 3. So the point is minus 3, 0. So minus 3 is equal to 0 plus c. Therefore, the c is minus 3. And therefore, this is simply y equals 4x minus 3. There's the equation of my tangent. Okay. However, they didn't want the tangent. They wanted the equation of the normal. So the gradient of the normal will have to be not 4, but minus a quarter. Y equals minus a quarter x plus c. And since we have to substitute the same point in, which is the 0 and minus 3 point that we had originally, we'll say that minus 3 equals minus a quarter x plus c, which is 0, so that's still c. So therefore, it is minus a quarter x minus 3. So let me just erase this and put in the minus 3. And there you have the equation of the normal. Alright, so nothing should be terribly much more difficult over there. Okay, you should be able to work out pretty much all of those sums. Do as many of them as you need to in 14a. Then we're looking at 14b, which now brings us to something called stationary points. Now, stationary points or stationary values are simply at the point where the gradient of the equation is 0. Okay, so if the gradient is 0, we have a stationary point, or we have a horizontal tangent if you want. Okay, so if there's a curve, and let me just draw you one quickly on the screen here. Okay, so say I have a curve that does something like this. Okay, and I draw tangents to this curve. I'm going to use red, and I'm going to use my ruler. Okay, if I take the ruler and say, okay, let's draw a tangent. Here's a tangent that we could draw there. Boom. But I could move the ruler, and I could also draw a tangent at this point over here. Touches that curve. And then I could also draw a tangent down here because it touches at the bottom. Can you see? Now this tangent that I've just drawn now, can you see is horizontal or has a gradient of 0? So that point at which that happens on that curve, okay, so in other words, this point over here would be considered a stationary value because the tangent that is drawn there has a gradient of 0. Okay, so let's have a look now and see what the sums look like for this. If you look at question 14b, number 1, they say find the values at which the following function would have a stationary value. So the function that they give us is simply x squared plus 7. We know that the gradient function, or the gradient of this function, would be 2x by differentiating. And if we wanted to know where that gradient would be 0, we'd have to say that 2x would be equal to 0. That means that x must be equal to 0. So at x equals 0, we would have a stationary value. Okay, I'm also going to do number 6 of that sum, which is the x cubed minus 3x minus 5. Okay, so let's do that one quickly. X cubed minus 3x minus 5 is the function. Its gradient function, let's just make it y, it's easier just to write. Its gradient function would be 3x squared minus 3. Now if I wanted to make that equal to 0, we'd say that 0 equals 3x squared minus 3, and that would mean that I could factorize 3 out and have x squared minus 1. Alright, that would mean that x minus 1, x plus 1 would give me 0. Sorry, that's a 3 over there. And that means that the x values for where I'd get a 0 are 1 and minus 1. So I'd get two answers here, x equals minus 1 or 1. Both of these values would give me a 0 gradient for the tangent. And that means that at x equals minus 1 or 1, I would have a stationary value. Now that's the values of x. If you look at the question number from number 13 onwards, they don't ask for the value of x, but they ask for the coordinates. Well, if I get the x value in the same way that I've done, but then substitute the x value into the original equation, I'll get the y value, and that will give me a point. So if they had asked me instead, for this question, what was the coordinates? I would put in the -1, get -1 cubed, which is still -1, times -3 times -1, which is +3. So that's -1 plus 3, which is +2, and 2 minus 5 is -3. So at the point -1, -3, there would be a stationary point. That would be the coordinate. Okay. So none of those sums in 14b should also be difficult as long as you can differentiate. So just the last ones are a few more difficult differentiations, but you should still be able to substitute things in and solve for the answers. So try exercise 14b. And then we're going to move on to 14c. Okay, so we're going to ask ourselves the questions, okay, of the nature of the stationary point. Now, let's have a look again. I'm going to draw that lovely curve I had on now. I'm just going to draw it a bit bigger here. Remember, we said that if we worked out the tangents, there would be a place, for example, over here where there'd be a stationary value. Okay? Or if you want, we can call this a turning point. But now notice in this curve that I've got, there's also a stationary value over here. Sorry, let's move it down a little bit. There we go. Now, the question I'm going to ask are these stationary values the same? Okay, not just in terms of points, but are they the same type of thing? Because there will be a point over here where I'll get a gradient of 0, and there'll be a point over here where I'll get a gradient of 0. But if you look at this one here, the curve comes down and then up. It makes a dip. But here, it goes up and then down, okay? It makes a bump. So we call this one a local minimum. Why? Because once it hits the bottom, it turns up again. Here, we call this a local maximum. So both would give me the answer 0. Remember in that previous sum I did, we got a -1 and a +1 for our sum, okay, as the x values. And that was a cubic curve. So this could have very well been this curve that I worked on. So let's just use that quickly. At -1 then, we would have had a local maximum, and at +1 in this case, we would have had a local minimum, okay? The curve would have curved upwards at +1, but at -1 it would have curved downwards, okay, or made a high point rather than a low point. So we want to decide mathematically now if we can decide what these points would be without drawing the curve, whether we would have a local maximum or a local minimum. And so we're going to give a method for doing that, okay. Now, the textbook suggests various ways of doing that. In fact, it suggests 3 methods. I'm actually only going to really do one method because there's not much point in doing the other ones. So we're going to just look at a method of solving these stationary values for whether they are maximums or minimums. And that method that we're going to use is something called using the second derivative. Okay. So let's have a look at a curve, okay, and I'm going to draw one quickly, or just the curve of the equation of one. Let me erase this for you. So I'm going to look actually at the example 14c, which is on page 166. They give us an equation y is 4x cubed plus 3x squared minus 6x minus 1. So let's write that on. 4x cubed plus 3x squared minus 6x minus 1. Differentiating that would give me 12x squared plus 6x minus 6, which I can factorize 6 out of and simply get 2x squared plus x minus 1, which I can also factorize. And that would be 2x minus 1, x plus 1. Minus x plus 2x gives me the positive 2x that I want in the middle. Okay, so that means that I have stationary values because I could make this gradient 0 at the point where x equals a half, because a half in here would make that bracket 0, or x equals minus 1. So we would add stationary values at those 2 points. Okay. But now, like we said, we want to discuss whether those stationary points, which one is the high and which one is the low, or are they both high or are they both low? Generally, if one is high, one will be low, so there's never normally a case of both. But we want to find out what is true about these. So we said we're going to use something called the second derivative. Now, second derivative just means we're going to derive the derivative. Okay, so we'll write y double prime. Let me erase some stuff here so I've got some space. So what is the second derivative? Well, if I derive 12x squared, I'm going to get 24x. 24x plus 6, yes? All right, and so 24x plus 6. Now we've already found the x values at which the points occurred, the stationary values. If I put the values of x as a half and x is equal to minus 1 into the second derivative, I'm going to get two different answers. The half will give me 12 plus 6, which is 18. And if I put the minus 1, I'm going to get minus 24 plus 6, which is minus 18. Now, the important thing about the second derivative value is not what the actual answer is, but whether it is positive or negative. Okay? Now, for the x is equal to a half, we got a positive value of 18. That means that the place at x is equal to a half is a minimum. And if I get a negative value, it means that at minus 1 we have a maximum. Now, let's have a look at what that means. So remember this, when I find the second derivative and I plug in the values of the stationary points, if I get a positive value, I have a minimum. If I get a negative value, I have a maximum. So what does that actually mean? Well, let me now keep this information of which one is minimum and which one is maximum, and let's have a look at what the curve might look like. So what we found was that this is firstly a cubic curve. If I drew it, it might look something like this. We know it'll cut at minus 1 because that's the C value of the curve, so it'll cut here. We know it's cubic and that it's positive, so that means that the cubic curve must do that. We know that there are stationary values where x is a half and where x is minus 1. Okay, so half is about here, minus 1 is then about here, and these are stationary values. And we know that the minimum one is at a half. That means that the curve must go down like that at the point a half, but up like that at the point minus 1. That means that my curve pretty much must look something like this. Okay, there it is. Now, I don't quite know whether this point was lower down here somewhere or maybe up there. I don't know that. Okay, but I can at least say that this is the looking of the curve. Well, we can actually find out where that curve cuts at half, okay, by putting the half into the function here. Okay, I'm not going to do that right now. It's lots of calculation, but they might ask you to do this a little bit further along the road now. Okay, so if you look at questions 14C, okay, they ask you to find the stationary points and then distinguish between them. Okay, in other words, which ones are positive and which ones are negative. Now I'm going to do the first one for you as well, and so we're going to look at number 1, which is the function 2x minus x squared. 2x minus x squared. Its derivative is simply y is equal to 2 minus 2x. If I make that 0 or equal to 0, okay, so y prime is 2 minus 2x, we'll make it equal to 0. We then get that minus 2x equals minus 2, which means that x equals 1. So a stationary value occurs at the point x equals 1. If we derive it a second time now, we get the answer of minus 2. Now, that is negative. So what we can say is that at the point x equals minus 1, since the second derivative is negative, it means we have a maximum occurring. Okay? And listen, if you drew that curve, it's a quadratic curve with a negative x squared, it would look something like that. It would have one turning point, which is a maximum you can see on the graph, and that will, we can tell, occur at the point x equals 1. because that's where the stationary value occurs. So the picture of drawing that curve tells us all of this information, but we've just solved it mathematically. All right, so you're going to be asked now to go and solve for some stationary values. Now, just one other last point, there might come one or two questions where when you do the second derivative, d2y over dx squared, or y double prime, these are all terms for the second derivative, okay, you might end up saying that now the second derivative is neither negative or positive but comes out 0. When you get a 0 for a second derivative test, okay, then you don't have a maximum or minimum turning point, but you have something called a point of inflection. Okay, so this is something to remember as a new term, and what that means is that the curve doesn't do that or doesn't do that. What the curve does is it might go up and then just make a little dent and then go up again. So that point would be where the point of inflection is. Okay, so it's not quite a turning around. It might be that that point of inflection could literally get to 0 and then go up again. So it could be quite flat there. You could have a tangent of 0. Or it might be that there's actually no tangent, and so it just makes a slight dip, but you would still get a point of inflection in the curve. Okay, so when you have a second derivative equal to 0, then you don't have a maximum or minimum turning point. You have an inflection point in the curve. Right, that takes care of up to 14 point C, and like I say, you should have actually got there. I've just done a couple of examples now to show you. If you look at the other video, you should also see some of that. We're going to look at the application section in the next video, which is exercise 14D, and I'm going to work through some of those problems a little bit more thoroughly with you, and then we're going to be on to the mixed exercises, which I'll also do. That will be video number 3, and we'll finish this chapter. Once we finish that chapter, we will start a section of work on trig in chapters 15 and 16. Enjoy the rest of the day, and I'll be in touch with you online on Zoom so that you can ask questions at some stage.